Greetings everyone. As always, I would like to start with a brief disclaimer. These videos are meant to help people learn physics. At times, it's meant to provide helpful hints, and at other times, it's meant to take you through the entire problem with hopefully what is a decent explanation so you can solve many others on your own. I try my best not to show the entire answer in any one screen so that the video remains about learning how to solve the problem and is not something simple that can be used as a shortcut to cheat or get ahead. If you're putting up with the sound of my voice, clearly you must want to learn this material. Okay, let's get started.
This question is talking about a car that's rounding the top of a hill. So the first thing we should do is just put up what we know, maybe in terms of visual diagrams and some equations, and not worry so much about solving the problem, but think about what does the problem tell us and what is it that we as students of physics already know about the laws of physics concerning this problem. So let's get started. I'll start with a simple diagram. I'll draw an imaginary hill and I'll put a car on it. There we go. That's a good looking car. And yeah, think about what do I know? Free body diagram. I mean, even before I look at all this stuff, I know that if there's a car on top of a hill, there's the force of gravitation acting on it. Free body diagram, right? And the hill, the ground, is pushing up on the car, so there's a normal force. And really, those are the only two forces at this point that at least the problem talks to us about. It doesn't really speak to us about friction yet. So that's our free body diagram. And then there's some facts given to us, like the mass of the car is 950 kilograms. What else do we know? The radius. Okay, so this hill is somehow nice and circular, and if you take the radius of this hill, that's not a perfect circle, but if you take the radius of this hill, they say that it is 95 meters. So that's something we know. We know the velocity of the car just when it's at the very top. It's 22 meters per second. And what else do we know? That's about it. Okay, so now they want to know the normal force, which is F of n, that the road, how hard does the road push up on the car? That's question number one. And I myself get very confused here because I know there's a third hypothetical force, hypothetical only because it's not a real physical force, which is the radial force, F of r. That's at play here, but it's not like anybody's pulling the car. This force is more of a observed relationship. It's nice because it gives us an equation to find, gives another equation to look at the same situation. It's just that it's more of an observed, if I push this, then that happens. So it's not a direct cause. There's nothing truly pulling the car in a circular or semicircular motion. It's more of an observation. Hey, it kind of behaves along these, parameters. It behaves like so. One can say that, you can go on to find this mathematical relationship about how objects move when they're in a circle. So, right here, it's not a real force. There's nothing pulling the car. The car is driving itself, and it just happens to be on a hill that's nice and circular or semicircular. So it does not belong in a free body diagram, and a lot of physics professors, I imagine, would deduct points if you were to put it somewhere on the free body diagram. So I asked myself this question: how do I resolve this? Before I even begin solving this problem, how do I justify using this equation? Well, I came up with an idea that sits quite well with me, and I hope it will sit well with you as well. So, sum of all forces in the y direction. Now there's principle of physics, that takes two variables and says this is how they interact, and that's what determines forces, right? Mass times acceleration equals force in the y direction, right? Now the car isn't flying up, so we know the acceleration here is 0. Now that happens to be a real physical force, right? Mass times acceleration of gravity due to gravity. But it could also be somebody pushing the car up, like the ground. So what it becomes is, there's another equation, which is more about an observed principle. And that equation is that the sum of an object moving in circular motion is actually that radius. Sometimes I switch between lowercase r and uppercase r, but I actually just mean to write radius. Forgive me for not staying consistent. So let's think of it as two separate systems. We know one system of equations would say force of gravity plus the opposing direction, because normal force is going in the opposite direction, and probably should just say how we plan to do this. There you go. That's going to be equal to 0, right? But we also know that, or rather, let's not write it like that. Let's write it like this. Oops, give me a second. Let's write it a little differently. So I choose to write it like this. I just ignore the MAY going to 0. I just say, oh no, fg plus minus f of n is sum of f of y. And I also know that there's another way to get at this for, which is not a real force, but hey, the equation works, and that equation happens to be this that's just the observed principle of how objects move and how the variables correspond to how those objects move when they happen to be moving in a circular motion. Okay, so I know this to be true, and I've observed this to be true even though it's not a physical force, but you pull this, that thing gets pushed out. Such is life. So these two are the same, so then I'm able to wrap my head around why I end up with this equation, which earlier I wasn't happy with, because I used to rely on free body diagrams, and force of radial, force of a circle being, object being pulled inward towards a circle is not a real force. So this is how I reconcile my problems with radial force not being a real one. Okay, it's just a formula, and it happens to live on the other side, and when things walk that path, they behave in that manner, so they go on the other side of the equation, and the left side of the equation is still a nice free body diagram that's real and rooted in the true physical world. So a lot of you might have had that question. If you didn't, hopefully you skipped this entire explanation that I gave. And so let's do it. Force of gravity is mass times acceleration, so that's 950 kilograms mass times acceleration due to gravity, minus normal force equals mv square over r. So 950 kilograms times, I'll make my life easy, and instead of 9.81 meters per second square, I'm just going to use 10, because the numbers work out easy for me. I'm a human, I'm not a calculator. And let's see. And oh, I jumped the gun, didn't I? So let's see, I'll undo some of this. I should show all the steps. Okay, minus f of n equals mv square over r. Again, okay. So let's bring mv square over r on this side, and let's send f of n on that side. So we end up with just mv square over r will be subtracted from 950. I'm going to take the units away, times 10. And f of n becomes positive on the other side. And, if you keep going with that, what do we end up with? Let's see. Keep going with that, then this is minus 950 times, the speed was given to us as 22 meters per second squared, and the radius was given to be 95 meters. I'm gonna stay away from the units again, and that gets subtracted from something big like this. So that's what, 9500 minus 4840, and they're both in newtons, equals f of n. So what is f of n? F of n works out to be something like 4660 newtons. And we really had two significant figures in this problem, right? 950 had two significant figures, 95 had two significant figures, really just one of them has to have two significant figures to cause everything else to be dumbed down. So we'll say this is rounded to 4700 newtons. That's the normal force. And it's applied, of course, upward by the ground on the car. If you did this whole problem using 9.81 meters per second square, you would get something like 4500 newtons when you round it, because I did the math a little bit earlier and it came out to something like 4479.5, and again rounded to two significant figures. So you can, if you use 10, you end up with 4700 newtons rounded to two significant figures. If you use 9.81 meters per second square for gravity, you end up with 4500 newtons. Not a big deal. So hopefully that makes sense. All right, part B, normal force exerted by the car on the 72 kilogram driver. So initially they gave us, the mass of the car, and now they're giving us the mass of the driver. That's interesting. So now they just want to know, hey, you told me what the normal force on the car was, now tell me what the normal force by the car on the driver is. So, because the ground is pushing the car, and technically the driver isn't sitting on the ground, the driver is sitting on the car seat, so the car is pushing on the driver. So hopefully that's not a surprise. But there's nothing really crazy going on here. It's the same thing if you think about this. There's mass times acceleration due to gravity, right? That's the driver, m of d, right? Mass of driver times acceleration due to gravity. And I'm just going to jump a little bit, because we already found that, or we already reconciled that we can subtract from that the circular motion. So mass times mass of driver times v squared divided by r radius is equal to the normal force on the driver. If this is not making sense, then I'll do it again. There's the car seat pushing up on the driver, that's the normal force. There's the force of gravitation, and that's all there is. Just like the car is going in a circular path, the driver on the car seat is going on a circular path. So the observed principles or mathematical equations that are at play here happen to be, one of them happens to be this, radial happens to be this. So you take this is one set of equations coming from your free body diagram, and this is another set of equations coming from mathematical observations, or more like practical observations turned into math. And you just say, oh, this and this must be equal, so I'm going to substitute. And you say mass of the driver due to acceleration due to gravity, which is f of n minus normal force, and that comes from this comes from this, and v squared over r. So you say normal force, I don't know what that is, but this is what's going on. And then this translates into this translates into this, and then mv squared gets subtracted, f of n becomes positive. It's really the same exact work, only now with the driver's mass. The physics or the math behind it hasn't changed by much. So 72 kilograms, I'm skipping units. This time I'll use 9.81. 72 kilograms, speed of the driver is the same, also 22 meters per second, and that will get squared. And the radius of the hill is still the same, it's still 95 meters, that hasn't changed. Although somebody might say the car seat is a little higher, so I'm not gonna get into that. So 95 meters force on the driver, normal force on the driver, and you do the math, and hopefully you end up with something like 340 newtons. Just, there's nothing magical or complex about that. If I use the calculator incorrectly, you will have a different answer. Leave a comment, tell me to fix it, etc. Again, two significant figures, right? Same problem, part C. The car speed at which the normal force on the driver equals 0. So now they're saying how fast should the driver go such that the car is just about to take off the ground. It's going to just fly into the air. The driver is going so fast, right? So we've been working on this equation for a while. So let's just see. So we want the mass of the driver and acceleration due to gravity. This is a bigger number every time than this one, right? That's why we end up with 340 newtons. They're saying, how could we increase this speed so much that the normal force would be just about 0? The driver would feel like he or she is weightless. So the real question is, how much can we pump this R up by? This is just the up arrow. It's not a real, just imaginary arrow showing that we want to pump this value up so high that, because the radius of the hill isn't going to change, we're not going to start digging or start adding to the hill. The mass of the driver is not going to change. He's not going to start eating or dieting. We just have to speed up the car such that the normal force goes to 0. That's the question. So, there's only one unknown. Mass is known, radius is known, and I meant to write v velocity here. How can we pump up the velocity? Yeah, so just solve for it, and we'll get it. So let's try 72 times 9.81 meters per second square, 72 times some imaginary velocity, radius is 95 known, and this all has to go to 0. You can factor out 72, divide everything by 72, and 0 divided by 72 is still 0. So you end up with 9.81. So really what it's asking is, how much can we pump up the speed by so that when divided by the radius of the circle or the radius of the hill, it would be close to 9.81. Actually, it would be exactly 9.81. And we just do our math. 9.181 goes to the other side. And how to do this? Let's think about it. Well, it gets multiplied by 95. The minus goes away, and you square root the whole crazy thing, and you get something like 30.5 meters per second after the square root. And you have to go back to two significant figures, so that's 31 meters per second. So if you go this fast, if you drive this car this fast over that hill, you as the driver will feel weightless. All right, thanks for watching.